Welcome to today's deep dive. I was thinking the most important part of a multi-million-dollar yacht isn't the roaring engine or, the carbon fiber hull or the state-of-the-art navigation system.
Right, yeah. Most people look straight past it.
Exactly. It is a single, deceptively simple, flat board at the very back. Because when you picture a vessel cutting through the water, your eye is naturally drawn to the bow slicing the waves, right?
Oh, sure. Or the shiny hardware on the console.
Yeah. But today, we're looking right past all that glamour. We're doing a deep dive into the unsung hero of aquatic propulsion.
The transom.
Yes.
The transom.
Our mission today is to uncover how this specific structural barrier fundamentally dictates a vessel's survival and its speed, and honestly, your safety out on the water.
Absolutely.
We are pulling all of this from a highly comprehensive boating equipment catalog from Yacht Supply 24. Specifically, we're focusing on their technical breakdown titled, What is a Transom on a Boat?
And it's such a crucial topic because, well, it is the literal backbone of the vessel.
Right.
I mean, without a highly engineered transom, you do not have a functioning motorized boat. You just have a heavily compromised floating bathtub.
A very expensive bathtub.
Exactly, because every single ounce of thrust that moves you forward is channeled entirely through that one specific plane.
The physics of that are just staggering when you really break them down. I mean,
Yeah.
before we can even look at what materials go into building a transom, you have to conceptualize the intense physical forces it's designed to withstand.
Oh, the forces are massive.
Right. Its core functions are far more complex than just, walling off the back of the hull. Because in rough conditions, the entire hull is subjected to immense torsional stress.
Yeah, it actively wants to twist and flex.
Exactly, it wants to bend. So the transom acts as this crucial rigid barrier. It ties the port and starboard sides together to prevent that sheer flex and keep the vessel's structural integrity intact.
What's fascinating here is the sheer scale of the invisible kinetic stress converging on that single surface. Because the transom is fighting a brutal, relentless war on two completely different fronts simultaneously.
Two fronts.
Right. So from the outside, you have the chaotic, unpredictable force of hydrodynamic drag and crashing waves slamming inward.
Just constant pounding.
Constant. But the real violence is happening on the inside. You have the mechanical thrust of a heavy, violently vibrating outboard engine pushing into the vessel, trying to drive it forward.
The forces are almost contradictory. If you think about it, the propeller is trying to push the bottom of the transom forward, right?
Yes.
While the sheer weight and torque of the engine head is essentially trying to lever the top of the transom backward.
It's a constant twisting motion. It's wild.
It is. Think of it like human anatomy. A transom functions almost exactly like the human pelvis and the lower spine.
Oh, that's a great way to put it.
Right.
Yeah.
Because it connects the two sides of the body, the hull in this case. And it has to hold up the heaviest moving part, which is the engine,
Right.
while simultaneously absorbing all of the shock, impact, and vibration when you are running hard through a chop.
That structural analogy holds up perfectly because it must act as the sturdy base that securely mounts that outboard motor. And it isn't just holding weight.
It's doing so much more.
It's absorbing and perfectly distributing the immense pressure generated from rapid acceleration and, tight, high-speed turns.
Right.
Because if the transom fails to distribute that pressure evenly across the hull, the boat literally loses its center of balance.
And the steering just goes.
The steering becomes completely erratic, and furthermore, there is the basic requirement of water protection.
Oh, yeah. Keeping the water out.
Exactly. A perfectly sealed transom blocks following seas from swamping the deck, and it maintains the absolute integrity of the engine mounts to prevent slow, disastrous leaks into the bilge.
Wow. To put that localized kinetic stress into perspective, a transom's job is essentially like trying to hold a heavy industrial jackhammer against a brick wall
Oh, man.
while you are standing on an ice rink.
That is a terrifying visual, but yeah.
You have massive thrust, violent vibration, and zero friction beneath you. That specific combination of extreme mechanical and aquatic stress means the tolerance for failure is incredibly low,
Practically zero.
which dictates that the materials holding it together have to be, well, virtually indestructible.
Which is why modern manufacturers lean so heavily on specialized composite materials, primarily fiberglass reinforced with highly engineered marine resins.
Right.
Fiberglass has really become the unquestioned gold standard for a very specific mechanical reason. The glass fibers themselves provide incredible tensile strength.
They resist being pulled apart.
Exactly. They resist being pulled apart by that lever action of the engine we talked about. Meanwhile, the resin matrix cures into a hardened shell that handles the compressive strength.
Resisting the inward push of the propeller.
You got it.
And crucially, that chemical resin matrix is highly water-resistant at a molecular level.
Oh, absolutely.
It creates this impervious barrier that just won't rot or degrade when exposed to the elements over time.
Yeah, it's incredibly durable.
That combination of impact resistance and low maintenance makes it the obvious choice for longevity. But the Yacht Supply CUMI4 catalog also highlights aluminum, which is fascinating for totally different reasons.
Right. Aluminum's a whole different beast.
Yeah, it's heavily utilized in John boats and base boats because of its specific metallurgical properties.
It's incredibly lightweight.
Super lightweight, which allows those boats to have a very shallow draft, letting you get into, like, inches of water.
Right.
Plus, aluminum bends rather than shatters on impact, making it ideal for navigating rocky, shallow riverbeds.
Yeah, you don't want fiberglass cracking on a rock.
Exactly. And of course, it forms its own oxide layer, making it naturally rust-resistant in highly corrosive saltwater environments.
The material choice always reflects the specific operating environment. The lightweight durability of aluminum solves the problem of shallow water navigation,
Right.
just as the molded strength of fiberglass solves the problem of heavy offshore pounding.
But here is where I need to challenge the engineering logic of the source material.
Okay, let's hear it.
The catalog explicitly lists marine plywood as a common and viable transom material today.
Yes, it does.
If fiberglass creates this impervious, low-maintenance matrix, and aluminum offers lightweight durability, why in the world would anyone intentionally build a boat with a wooden transom now?
It seems crazy, right?
It really feels like deliberate obsolescence, inviting rot and failure into the most critical part of the boat.
It is entirely counterintuitive until you look at the strength-to-weight ratio. I mean, marine plywood isn't standard lumber.
It's not just a piece of pine from the hardware store.
No, not at all. It is a highly engineered composite in its own right. It is constructed from multiple thin plies of hardwood, and they're cross-laminated.
Cross-laminated.
Right, meaning the wood grain of each layer runs perpendicular to the next. This cross-graining distributes shear force incredibly effectively.
So it prevents the wood from splitting under the torque of the engine.
Exactly that. It handles the immense torque of heavy outboard motors while remaining significantly lighter than a solid fiberglass block of the same thickness.
Oh, wow. I didn't realize fiberglass was that much heavier.
Oh, it is. And for smaller fishing vessels and traditional wooden boats, keeping excess weight off the stern is paramount to maintaining a proper center of gravity.
That makes sense.
It is also exceptionally cost-effective. Now, while a plywood transom absolutely demands more vigilant sealing and maintenance to prevent water intrusion, its mechanical properties make it a highly effective engineering choice for specific vessel classes.
The ones that prioritize a lighter stern.
Exactly.
That makes perfect sense. The cross-laminated structure essentially mimics the multi-directional strength of fiberglass, but at a fraction of the weight and cost.
Right, exactly.
So the material engineering dictates how much physical abuse the transom can take. But as we dive deeper into the catalog, it becomes clear that the actual shape of the transom dictates how the boat fluidly interacts with the water.
Oh, yeah. Form dictates hydrodynamics.
A flat transom, for example, provides maximum stability and a wide, secure mounting surface for multiple engines.
But the trade-off with a flat transom is hydrodynamic drag.
Right. There's always a trade-off.
Always. When you have a wide vertical surface moving through the water, it is highly stable, but it pulls a massive amount of water behind it, forcing the engines to work harder.
Yeah.
To mitigate this on certain hull designs, engineers use notched transoms. These feature a physical cutout section that lowers the mounting point of the engine closer to the waterline.
Which fundamentally alters the fulcrum point of the boat.
Yes, exactly.
By lowering the engine center of gravity,
Yeah.
you are bringing the thrust closer to the horizontal center line of the hull, which drastically improves handling.
It does.
It reduces the boat's tendency to roll and increases overall balance during high-speed maneuvers.
It optimizes the transfer of power. We also see the reverse transom, where the stern is distinctly angled forward, sloping down toward the waterline.
Sloping inwards.
Right. This design is incredibly common on modern cruising yachts.
Okay, let's unpack this reverse transom concept because this is where the fluid dynamics get really interesting.
Oh, the physics are brilliant.
The source material notes that this angled design reduces drag.
Yeah.
The physics behind this are just, wow. When a perfectly flat transom moves forward at speed, it abruptly leaves an empty space in the water behind it.
A literal hole in the water.
Yeah, and the water molecules can't instantly turn a 90-degree corner to fill that void.
Right, they just can't move that fast.
So they separate from the hull, creating a massive low-pressure zone, which is essentially a suction effect that literally pulls backward on the boat.
That low-pressure zone is the definition of drag.
Yeah.
By angling the transom, you are creating a smoother, more gradual pathway for the water to reattach and rejoin behind the boat.
Ah, I see.
It smooths out the laminar flow and drastically reduces that turbulent suction effect.
That's incredibly smart.
It connects directly back to weight distribution and overall efficiency, too. A hydrodynamically efficient transom doesn't just make the boat faster.
What else does it do?
It reduces the mechanical strain on the hull, it minimizes the torque required for steering, and it drastically reduces the boat's fuel consumption.
It's just aerodynamics, but applied underwater.
Exactly.
And the design variations shift radically depending on the primary function of the vessel. I mean, powerboats require these thick, heavily built transoms to support engine weight and manage that thrust.
Right.
But sailboats present a completely different set of hydrodynamic challenges. Sailboat transoms are usually much narrower to reduce drag at lower displacement speeds, right?
Yeah, they don't have huge engines to hold up.
Exactly. And they often hold the rudder assemblies instead.
Mm.
But even more extreme is the open transom design mentioned in the catalog.
Oh, open transoms are a masterclass in specialized marine engineering.
They look so wild.
They do. They're predominantly seen in competitive racing sailboats. Instead of a solid protective wall at the stern, the back of the boat is completely open to the water.
Which sounds terrifying.
It does, but in offshore racing, heavy waves frequently crash over the bow and flood the cockpit. An open transom allows thousands of pounds of water to instantly evacuate out the back.
Just wash right out.
Exactly, preventing the boat from sinking or capsizing under the sudden weight. It trades the protective barrier for instantaneous drainage and rapid water access.
The engineering completely abandons the protective wall because the necessity of weight shedding is more critical to survival in a race.
Yeah, survival over comfort.
Speaking of specialized variations, you also have swim platform transoms that extend horizontally beyond the stern for recreational boarding, keeping swimmers safely away from the propellers.
Very important for family boats.
Very. Then you have full transoms, which extend across the entire width and height of the stern, designed for maximum safety against following seas in treacherous offshore conditions.
Right.
And finally, vertical transoms, perfectly upright surfaces utilized primarily on heavy commercial workboats. They keep massive diesel engines perfectly level for maximum thrust efficiency.
Every variation is a highly calculated compromise. You are always trading a degree of speed for stability, or a degree of protection for accessibility.
Always a trade-off.
Always. But because the transom is engineered to perfectly balance these immense mechanical and hydrodynamic loads, the tolerance for failure is virtually zero.
Zero.
And that brings us to the critical necessity of structural maintenance.
The silent threat.
Yes.
Because if your transom fails under load, you aren't just looking at an inconvenient breakdown. You are looking at catastrophic, life-threatening danger.
It's terrifying.
The catalog lays out the immediate consequences of structural failure. Sudden engine detachment, massive water intrusion, a total loss of hydrodynamic balance, and completely compromised hull integrity.
And the scary part is, the warning signs are frequently subtle. They're masked by layers of gel coat and paint. You have to actively look for them.
What are we looking for?
The most common indicator is soft or spongy spots, particularly on fiberglass or wood core transoms.
Spongy spot.
Right. A soft spot is a glaring mechanical failure. It indicates internal wood rot or structural delamination beneath the surface. You also have to closely inspect for stress fractures or spider cracking in the gel coat.
Specifically radiating outward from the engine mounts, right?
Exactly.
Those cracks mean the violent micro-vibrations of the outboard motor are literally tearing the fiberglass matrix apart at the molecular level, compromising the tensile strength we talked about earlier.
Exactly that.
And of course, you look for water leaks, rust weeping, or discoloration around the bolts, which points directly to a failure in the marine sealant.
Yeah, if you see rust weeping, you have a problem.
So what does this all mean? The way I see it, ignoring a subtle soft spot on a boat's transom is exactly like ignoring a termite problem in the foundation of your house.
That is the perfect way to look at it.
It might look perfectly fine on the outside, and you might comfortably go about your day for months. But the very second you introduce real heavy stress, like a hurricane hitting your house or hitting a 6-foot wave at 30 knots on the water, the compromised structure simply collapses under the load.
If we connect this to the bigger picture, it becomes evident that transom maintenance is a critical, non-negotiable safety protocol.
Absolutely non-negotiable.
Water exposure physically weakens the boat's skeleton. When water breaches the sealant, capillary action draws it deep into the fiberglass or wood core.
It just sucks it right in.
Right. And if that water freezes during winter storage, it expands, physically jacking the composite layers apart in a process called delamination.
Oh, wow.
And salt water accelerates this destruction exponentially. As salt water intrudes and evaporates, it leaves behind salt crystals.
And what do the crystals do?
They expand. They physically crush the internal cell structure of wood cores while simultaneously corroding any internal metal bracing.
It is a chemical and mechanical breakdown happening completely out of sight.
Completely hidden.
If you allow the core to rot and weaken, the sheer leverage of the outboard engine could literally rip the stern completely off, dropping a 1,000-pound motor straight to the ocean floor and instantly flooding the vessel through a massive hole in the back.
Which is why early detection and preventative maintenance stop these failures before they ever happen on the water.
So what are the protocols?
The protocols detailed by Yacht Supply 24 are straightforward. You must physically inspect the transom by tapping it with a phenolic hammer.
To listen for hollow, delaminated spots.
Exactly. You must routinely rebed and seal all engine mounts, scuppers, and through-hull fittings with marine-grade polyurethane to stop water intrusion. If you operate in a marine environment, you must rigorously flush the transom with fresh water after every use to dissolve and remove those corrosive salt crystals.
That makes sense.
Applying advanced anti-corrosion barrier coats can also drastically extend the lifespan of metal and composite materials.
When you really synthesize all these mechanics, it forces you to look at the back of a hull with an entirely new level of respect.
It really does.
We have gone from viewing a simple flat surface to understanding a highly engineered, stress-absorbing hydrodynamic shield. It is the architectural keystone holding the entire kinetic energy of the boat together.
It absolutely is. But, as we were analyzing the vast index of the source material from Yacht Supply 24, something highly disruptive stood out in their catalog sections.
What was that?
Amidst the hundreds of traditional structural mounts and gas outboard parts, they feature extensive, prominent listings for modern electrical propulsion.
Electric motors.
Yeah. We're looking at brands like Waterworld electric drive motors, Alamarinjet water jets, Metech, and Wolong electric outboards.
The marine industry is aggressively pivoting toward electrification and integrated water jets, closely mirroring the automotive sector.
Right, and that pivot raises a profound, lingering question regarding the future of naval architecture. The traditional, heavily reinforced transom we just spent all this time analyzing evolved almost exclusively to support massive, violently vibrating external combustion engines.
Right.
So what happens to boat design as the industry shifts entirely toward lightweight, hull-integrated, practically silent electric water jets and internal pod drives?
That completely eliminates the two-front war.
Exactly.
If the propulsion is integrated into the bottom of the hull, there is no longer a massive external weight acting as a lever against the stern. And there are no violent engine vibrations trying to tear the fiberglass apart.
Precisely the point. If the propulsion system no longer weighs 1,000 pounds and no longer relies on a vertical mounting surface to generate forward thrust, will the thick, heavily reinforced transom eventually disappear entirely?
Wow.
Will the fundamental shape and layout of recreational vessels completely transform when that heavy lifting is no longer an architectural requirement at the stern?
That is a staggering thought. If the engine evolves to be integrated and weightless, the spine of the boat has to evolve with it.
It has to.
The transom might revert to just being a hydrodynamic tool to shape water, rather than a structural shield.
It's entirely possible.
The next time you are walking down a marina dock or you see a vessel on a trailer, don't just look at the carbon fiber bow or the dashboard. Take a walk around to the back and truly appreciate the incredible physics and engineering of the transom while it still looks the way it does today. Thank you for joining us on this deep dive into the hidden architecture of the water. We will leave you with that futuristic thought to mull over. Keep exploring and stay curious.